A little thing about WebAssign. I think most people are able to use it just fine, but I do get a lot of emails about sort of technical issues with it, which I don't know the answer to. Like it's questions for WebAssign. So if you have questions about technical issues, try asking WebAssign support first. Apparently they're like a East Coast company, so they're on East Coast time, and they leave work at 5, which is 2 in the afternoon over here, so that's kind of annoying. Sorry about that if you have to wait until the next day to actually hear from their tech support. And let's see, about the homework. So one thing I put on the syllabus for this class was some tips for success. And one of them, obviously, is come to lecture and do the homework. But other ones include going to discussion and also the Learning Center and tutoring and office hours. Because I want to point out, you're not meant to be able to learn everything you need to know for the homework in class. You're supposed to have to struggle through some of it and go through some pain in order to learn it. Kind of like if it's not painful, then you're not really learning, probably. So on some of the problems, you're going to have to struggle a bit. And what you really should do is, if you're finding yourself not able to understand the homework or complete it, you need to be going to discussion and office hours and get help and get tutoring. It's possible, and sort of really the best way, I think, to learn is to just struggle with a problem, and if you still can't figure it out after like really trying for a while, then ask someone. And that's sort of how the learning process in your head works. When you struggle with a problem and then eventually figure it out, that really sort of ingrains the process in your head. So that's a good learning technique. Like me, I tutored for many years, and the way I would teach, I wouldn't tell kids the answer. I would make them tell me the answer, and I would give them as little help as possible, just sort of gradually giving them hints until eventually they figured out the answer themselves. So yeah, you're just going to have to do the problems, and that's the way you learn. And all that said, I will give you some hints on the homework. So for example, today at the end of class, I'm going to talk a little bit more about solids, because I've heard some people have been struggling with that. But let's start off with a new topic. It's a new technique of integration. It's called integration by parts. I'm curious, does anyone already know how to do this? All right, yeah, so some of you guys have seen this. It's a new trick in our book. About half of this class, which is devoted to integrals, is devoted to tricks for solving integrals. So we've already learned some tricks, like the substitution. That was a trick we learned that made integrals that were formerly not solvable now became solvable once we learned substitution. And I taught you guys, or I pointed out that substitution you could think of as the chain rule in reverse. So, kind of like that, here's another trick, and it's another certain rule in reverse. Does anyone remember what is this the reverse of? The product rule. So this, yes, integration by parts is just nothing but the product rule in reverse. Okay, so let me refresh your memory on the product rule. It says if you take the derivative of a product of two functions, you first put it on the first function times the second, and then you also have to put it on the second, and then times the first. So that's the product rule for functions. For whatever reason, the standard terminology that we use in integration by parts is instead of F's and G's, we like to use U's and V's. So let me rewrite this using U's and V's. i.e., if U and V are both two functions of x, uv prime is equal to u prime times v plus v prime times u, i.e., how about I'll just write it just a few different ways to make sure there's no confusion. This is the same as du dx times v plus u times dv dx, or u prime v plus u times v prime. And now let me write it a third way. How about in the language of differentials, which is kind of this new notation that we've been using because it's well suited for integrals. This is going to equal, basically it's kind of like I'm going to multiply this expression by dx. So I'll get a u dv and a v du. And now what I'm going to do is integrate both sides of this expression and apply the fundamental theorem. Okay, so I'm going to get u times v is the integral of the derivative of u times v. That's where the fundamental theorem comes in, right? The integral and the derivative just cancel each other out. But according to this expression, that's the same as the integral of, u dv plus v du, which is equal to, let's write that as two integrals, u dv plus v du. And the final step, the only thing that basically, the only trick now is I'm just going to subtract this term from both sides. So the integral of u dv is equal to this minus this, minus the integral of v du. And that is integration by parts. Here. Which I will abbreviate by IBP. It's funny, in the research that I do involving partial differential equations, I still do this all the time. Like, you would be amazed at sort of how high up this formula gets used. And yeah, it all started when I first learned this when I was first taking 20B, or whatever the Glendale Community College equivalent of that was. Okay, just sort of to clarify any confusion, let me rewrite this without the language of differentials. It's usually written this way, though, and that's the way you're always going to see it. But I just could also write the integral of u of x, and if you remember, dv means v prime of x dx. That's equal to u of x times v of x minus the integral of v of x times u prime of x dx. Okay. And really the best way to get used to this is just doing problems, doing examples. And eventually you'll get a feel for it. So that's what we're going to do. Let's do our first example. How about the integral of x times sine of x dx? Now, I told you that this was a new trick. We only need new tricks for doing things that we formerly were unable to do. Yes? So what I did is I subtracted this term from both sides of this equation. So I just had a u dv left on one side, and then a uv minus this integral on the other. Does that make sense? Yeah, it's this equation if I subtract this term from both sides. So this is an integral. I mean, would any of you guys have known how to do this before learning this formula? I wouldn't have, unless you got really lucky and just happened to guess, which would make you ridiculously lucky. I would not know any other way to do this except integration by parts. So here's where the magic happens. First step in integrating by parts is to choose what are you calling u and what are you calling v, or actually, what are you calling dv? So I'm going to make dx my u. And I'm going to make sine x dx my dv. Okay, so let me just write that out. U is x. dv, here, let's write it here. dv is sine x dx. Now, if we're going to apply this formula, we need to figure out what is du and what is v. So du, if you take the derivative here, well, derivative of x is 1 dx. Here, I could say 1 dx if that helps, or just dx. And now this is kind of the hardest part, is you have to think of what's the antiderivative of sine x. That's negative cos x. So v is negative cos x. Okay, now we can just plug this into the formula. So the integral of x sine x dx is equal to, okay, formula says u times v, so that's this times this, x times negative cos x, minus the integral of v, which is negative cos x, times du, which is just dx. So this is negative x cos x, minuses cancel, plus the integral of cos x. And sort of the magical thing that happened here is this is an integral that we can easily do. We did not know, at least before this, no one should have known how to integrate this. We don't know it. It's not, we don't have any rule for that. But cosine, we can integrate. Integral of cosine is sine. So we get a negative x cos x plus sine x. And it's a good idea to just check. Oh, plus c. Let's check by taking the derivative of this. So the derivative, I'll get a negative 1 times cos x minus x, and the derivative of cos is negative sine x, and then the derivative of sine is cos x. This is negative cos x plus x sine x plus cos x. The cosines magically cancel out. Oh, x sine x. Was that our original integrand? It was. X sine x. Sweet. So we did it right. It works. Kind of magical, right? Like we got this expression. It ended up being just what it needed to be so that the terms canceled out and we ended up with exactly what we needed. I was impressed. Okay. By the way, this checking thing probably a good idea on a test, like if you have time. If you have time on a test and you haven't checked your answers, then you really should check your answers. So this is a good thing to do, just to make sure you did it right. Okay. Now, this all seemed fine, but I know what I'm doing, of course, right? Like I knew, well, for one, I knew that this was a integration by parts problem, right? Like, if you're doing homework problems and they're in section 7.1, it's a pretty good hint that that means it's going to be an integrating by parts problem. Now, if this was a, say, final exam and I didn't tell you what method to use, then it would be a little bit trickier. Here, at least we have the benefit of knowing what method we're supposed to apply. But okay, let's say we already know we want to try integration by parts. How did I know which to make u and which to make dv? That's the challenge, is making the correct choice of u and dv. And obviously I did it right because it worked. Let's see what would have happened if I had made a different choice. So continuing this example, let's see if it still works. Like, let's see if it matters. So what would have happened if I made a different choice of u and dv in the integral x sine x? So now, how about let's do it the other way. Let's let the, sorry, x sine x dx. Now let u be the sine term. And that means dv, here, right, okay, so like if, let me circle it. If this is u, then this is my dv. So dv is x dx. Okay, so now let's see what happens. Du, that's pretty easy. That's cos x dx. But what's v? Right, or x squared over 2. X squared over 2. Yeah. Yeah, the antiderivative of that. Okay, so fine. Then let's see what happens. Then the integral of x sine x dx, we can still apply the formula. It'll be u times v. So sine x times x squared over 2 minus v du, the integral of x squared over 2 times cos x dx. And okay, fine, this is correct, but what's the problem here? It's correct, but is it good? I just made the problem harder. Right? Like, I was trying to integrate x sine x. Now, okay, I've got this term, but this looks like an even harder integral to evaluate. This is supposed to make your life easier, not harder. Clearly, this is more difficult. Now it's got an x squared, and it's like if you couldn't do it with an x, and you definitely can't do it with an x squared. So yeah, this is not helpful. So we would not do the problem this way. Not helpful because x squared over 2 cos x is even harder to integrate. So how do you know when the choice of u and v is actually helping or not? Like basically, okay, I don't have a totally precise answer for you on that. Part of it just comes down to trial and error and experience, but I can give you a pretty good guideline is, does it make the integral look simpler? Right? Like once you do integration by parts, does what you get look easier? Now, It certainly did when I did it here, because this looked easier to integrate than this. And what I did was I was able to get rid of that power of x right there, was what made it look easier. So a general guideline, it's not going to be true in all cases, but in many cases, it's such that the resulting integral is, let's just say, simpler, i.e. has smaller powers of x, for example. So u equals x to the n for positive integer, for pause. Is usually a good choice, right? Like if you have powers of x in the integral, as I did there with x sine x, usually that's what you want your u to be. And the reason is because when you take du, right, you lose a power, so that's less x's usually in the resulting integral. And you might be getting a hint from this hint that I wrote that sometimes we have higher powers of x. Here we had 1 power of x. So let's see what would happen if we had an x squared. And we'll follow this guideline, but I'll have to take an additional step, is I'll have to do it twice. I'll have to integrate by parts twice. So what if we had x squared? Let's do x squared cosine x dx. According to the guidelines I gave you, what should u be? The x squared. Good. So we're going to make this my u, and this will be my dv. Okay, so now let's write it out. So u is x squared, so du will be 2x dx. dv was cos x dx, so that means v was sine x. Yeah, derivative cos. Okay, so therefore this thing will equal u times v, x squared sine x. Here, so this is the integrating by parts step, minus the integral of v du. There's my v, there's my du. So sine x times 2x dx. Okay, so this is x, oh, sorry, this is a x right here. This is x squared sine x minus, I'm going to pull the 2 in front, 2 times the integral of sine x dx. So you might be asking yourself, did I make things easier, right? Did I do it right? I didn't get really an elementary integral, but I did get one that actually we already did. Yeah, this guy right here was exactly my first example, which we solved by integrating by parts. So I kind of saved myself a little trouble here with this example by ending up with one where I already know the answer, but like in general, you would now integrate by parts a second time. So this is x squared sine x minus 2, and let's just plug in the answer that we already know. What did we get? We got negative x cos x plus sine x plus c. Negative x cos x plus sine x plus c. So this is using example 1, i.e. integration by parts, because that's what we did in example 1. So we get x squared sine x plus 2x cos x minus 2 sine x. Should I put minus 2c? Just c is fine. All right, good. Just plus c. And once again, I encourage you to take the derivative of this and make sure that you get back to x squared cos x. So, like it happened with substitution, we are now increasing our library of integrals that we are able to solve. Integration by parts is especially suited to problems like the examples that I've been doing. So I remember one student asked me when I was doing substitution, like, what if I just changed the problem a little bit, would I still be able to do it? And the answer is no. So again, right here, it's kind of like the problems deliberately need to be constructed to be amenable to integration by parts. But that's still a whole bunch of different problems which we formerly were not able to do. So note, some common integration by parts type problems they're basically, it's a power of x, positive power of x times cosine, a positive power of x times sine, or a positive power of x times, let's say, exponential. All of these guys are well suited for integration by parts. And in each one of them, the first step, oh, by the way, let me say n a positive integer. And in each one of these, this is going to be our u. So that's a whole bunch of new problems that we can now solve that we formerly were not able to. There's a yes.
Only unbounded integrals?
Yeah. Good point. I'll mention definite integrals in a second. But before I do that, let me ask, how many people have learned the shortcut way for doing these guys, where you draw the column? Has anyone seen this cool shortcut where it's like this is your U column and this is your DV column? And you do like plus, minus. Anyone learn this thing? One person's? Okay. It's this neat little shortcut that makes these, it's like a really fast way to compute these. I wasn't planning on showing it to you. I didn't really give that many problems, homework problems, where you need it. But if time does permit, maybe I will show it to you at some point. But I was just kind of curious how many people had seen that. But, okay, in fact, someone asked about the definite integral version. The definite integral integration by parts formula it's kind of like the indefinite one, except now we put limits. So I'm not going to go through the whole derivation. I'll just tell you. The integral from a to b of u dv, it's, well, without limits, it looked like this. So now let's put limits here, and let's put limits here. That's basically all that to remember. So here, let's just put it in green just to show you what's new. A, B. It looks just like the old one, except you put the limits there. So there's that formula. There's a couple more tricks that I haven't shown you. So let me do another example where that does not sort of fall into this category. Right? I said this was a guideline, which means it's not 100% all the time true. Sometimes you have to try something different. So here's an example where that won't work. Namely, how about the integral of ln of x? In fact, let's make this a definite integral just to sort of keep things definite and apply this formula. So the guidelines that I gave you don't help here because there is no power of x. Well, there kind of is. I mean, there's 1 is a power of x. So if you saw this integral, at first you should be stumped because you can't do it, right? Ln of x does not have an elementary antiderivative given what we've learned so far. So you start trying to think of tricks. Maybe you realize that, oh, this is a 7.1 question, so let's try integration by parts. And really, the only thing there is to try, well, there's kind of only one choice for what u could be. That's ln, which means this must be dv. So let's just see what happens if u is ln x. So du will be 1 over x dx. And if dv was dx, so v is just x, then we will get, OK, u times v is x times ln x minus, let's put our limits, the integral of v du, which is x times 1 over x, so we get 5 times ln of 5 minus 2 times ln of 2 minus the integral. Oh, hey, this is kind of neat. We get to cancel out the x's. So this thing is just the integral from 2 to 5 of dx, which is, anyone know what that is off the top of their head? It's just 3, right? Length of the interval. Or here, you could write it as x from 2 to 5, which is 5 minus 2, which is 3, if you want. So here, let's just put that in. So minus 3. OK, so there's an example of one time where you'll have to try something different. There's another problem. In fact, this will even come up on a homework problem. So on homework problem number 15, you have something like, I don't remember exactly what it is, but it was something like cos x e to the x or something like that, or maybe it was a sign or there was a negative here. I don't remember exactly, but in order to do this one, you'll have to integrate by parts twice and then recognize that, wait, you just got back to like the term that you started with. Then you have to move it to the other side. It's a trick that I'm not going to show you right now because I don't have time, but I'm going to point you to where to see how to do it. So it's an example in the text, example 5. So that'll be on you guys to do when you're doing the homework, is to see example 5 in the text. To see how to do this. Okay, let's see. I think okay. Now let me talk a little bit about a problem from the homework that is due tomorrow. This basically wraps up section 7.1. So let me go back a little bit to talk about solids. Someone pointed out that some students were having some trouble with some of these, so I thought I'd talk a little bit more about it. I have some time right now, so let's look at problem number 7 in 6.2, which was this. Sorry, problem number 6. Here's the shape that we're supposed to get the volume of. It's what would you even call that shape? A wedge, kind of. Some sort of wedge. A tetrahedron. It's a type of tetrahedron, I think. All right, it's got 1, 2, 3, 4 sides. Okay, so let's find the volume of this guy. Let's say this is at 8, this is at 4, and this is at 6. And the way we're going to do it is using similar triangles, which is probably hard for some people. You know what? I need to draw this bigger. Hold on. Okay, let's find the volume of this guy. So you have some choices in this, actually. We talked about how you can integrate dy or dx. Heck, I could even label this as z and integrate dz, but let's not make things more complicated than they need to be. So there's not really any one direction that's any more symmetric than any other one here, so I'm just going to integrate in the x direction and make this a dx integral. So let's take a slice of this. Let's just pick a point on the x-axis, label it x, and let's look at one of these cross sections, which is going to look like that. Now, the area of this cross section, what's the shape? Triangle. So we have triangular cross sections. With area A, which should depend on x, and the triangle formula, the triangle area formula, is 1/2 base times height. So if we can figure out the base and the height, then we'll have our area of the cross section. And the base, here's the base, B. Here's the height, H. So to figure out B and H, I'm going to have to draw some similar triangles. So let's start with B first. In fact, I'm going to draw the entire bottom of this shape to sort of make it more clear. It looks like this. This side of it is 4. This side is B. Oh, sorry. It's kind of upside down. This side is 4. This side is B. Now, this right here is X. Does anyone see from the picture what the whole length from here to here is? It's 8. So this here is 8 minus X. Okay, good. We now have enough information to set up a similar triangles ratio for this triangle, which I'll do right now. So let's do, how about short side to short side equals long, short leg to short leg equals long leg to long leg. Short leg to short leg equals long leg to long legs, because the whole thing here is 8. Any questions on that? So that gives us B equals 4 times 8 minus X over 8 equals 4 minus X over 2. Okay, great. That gave us the base. We actually have to do another similar triangles ratio to get the height, though, too. So how about for the height? Now, there's multiple ways you can do this. And in fact, there's even multiple ways you can set up the ratio. So don't think that just because you're doing it differently that it's wrong. You might just be doing a different similar triangles ratio. There's a lot of correct ways to do it, as long as you just remember to set up ratios of corresponding quantities. So for the height, let's see, what triangle do I want to draw now? How about this one? Okay. So let's draw that one over here. Okay, the height there was 6. This one was H. We already said that this right here was X. So this right here is 8 minus X, and the whole side was 8. Okay. So again, we can do short leg to short leg. Short leg to short leg equals long leg to long leg. It's kind of the language I used to use, and I would explain similar triangle ratios to my high school geometry tutoring students. So in this case, the two short legs are H and 6. The two longer ones, 8 minus X and 8. So H is equal to 6 over 8 times 8 minus X. That's 3/4 of 8 minus X. So that's 6 minus 3X over 4. Okay. Then the area, which I can now write as a function of x, right? That's great. I wanted all these quantities in terms of x before I plugged them into 1/2 base times height. So that'll be 1/2. B was 4 minus x over 2. H was 6 minus 3x over 4. This is going to be a pleasure to integrate. So here, we can just multiply this out, see what we get.
It's a lot easier if you leave 8 minus x as a common, and then you can just square it and then do so.
Oh, okay. So, all right, that could be an easier way to do it. Okay, so she's saying let's write this as 1/2. H was 3/4 8 minus x. B was 1/2 of 8 minus x. Okay, so what do we get? We're 3 over 16 times 8 minus x squared. Yeah, that is easier. Cool. So the integral of a of x dx, just checking my work here, 3, 16 minus x squared. And what are my limits for x? 0 to 8. Okay, so I will get the integral from 0 to 8 of 3 over 16 times 8 minus x squared dx, which is equal to 3 over 16. And following, what was your name?
Taryn.
Sorry?
Taryn.
Taryn?
Yeah.
Oh, cool. Okay. Following Taryn's suggestion of let's make this guy equal to u. So here, so this will be 8 minus x cubed over 3, and with a negative sign from 0 to 8, which is equal to 3 over 16 times 1/3 times 8 cubed. If I did that right. Let's just as a check. So look, once you've done a lot of substitutions, you kind of do them in your head. But just as a check, if I take the derivative of this, dang it, if I take the derivative of this guy, do I get this guy? Yeah, because I get a 3 cancels this, and the minus sign cancels this. So good, I did that right. And 8 to the 3rd over 16. That's 8 times 64 over 16. That's a 2. It's a 32. Okay, now on the homework on the web page, I don't know if you guys have read that carefully, but some of the problems in the homework list are written in bold. This is on the class web page, and there's a note that says these are problems that don't appear online on Wiley because they weren't available there, but you're still expected to know them for purposes of the tests. So one of them was number 7 in this same section, which is this same problem, except the only difference is instead of having lengths of 4, 6, and 8, there are lengths A, B, and C. So this is the problem, is to now find this volume in terms of A, B, and C. And you should be able to do it using this same method. So